So just a few words about the current market with availability and approaches to screening and process development tools. There's always a trade-off between experimental throughput and information content. So at one end you have microplates where there's a lot of capacity in terms of screening, but the information content here can be quite low. And then we have shake flasks. Again, this is a cost-effective method of screening, but again the information content can be quite limited. And at the other end you can go to litre scale, a possibility of screening multiple vessels, but here, although the information content, the sheer size, cost and the amount of material can make it quite restrictive in terms of having large-scale campaigns. So what we offer is kind of this sweet spot here where we can maintain a large amount of information from the bioreactors, but still have a lot of possibility for screening and having tools for process development.
Welcome to the webinar. You have entered as an attendee in listen-only mode.
So the key benefits of the system we're looking at are to speed up process development and optimization, to provide high information content and ensure that data is scalable, give a greater understanding of all the process parameters of the application, and to simplify gas management strategies which can be quite complex. So the Xplorer HT bioreactor system is composed of 4 main elements. The first is the frame. Now this is a highly configurable framework onto which you can place feeds, electronics and other resources needed by the bioreactors. Then we have the blocks where you can insert the bioreactors, and we have 2 possibilities here. We have a 4-zone block and an 8-zone block, and we can have combinations of these to give the capacity needed. We can actually process 48 bioreactors from a single software. The bioreactors themselves, here we have a range which I'll come to shortly. Typically we're looking at ranges of working volume between 20 and 375 milliliter. And then all the systems we actually produce are fully automated, and they all come with controlling software, which I'll also explore later. So to start with, we have the Xplorer Bioreactors. We have a range of reactors which will fit on the system. They're designed to be geometrically similar to large-scale vessels, as I say, with a working volume from 20 to 375 mil. We do have litre-sized vessels, not shown here. I'll come to it in the next slide, and so the system can be expanded to offer litre-scale processing if needed. All the sizes you see here are available in glass or stainless steel, and the stainless steel bioreactors are rated to 10 bar pressure, obviously making them ideal for pressure applications. Now, an important feature of any miniature bioreactor is to make sure that it's scalable. Here we've done some experiments on comparing miniature bioreactor, 100 ml working volume, with a more conventional size, 1.5 litres. And by keeping the KLA at the same value, we see that we get very similar specific growth rates and final biomass concentrations. So this gives us confidence that the data we're seeing at the small scale can be projected onto larger scale vessels. One of the key design areas is to ensure that we can get as much information out of the reactors as possible, and one important facet of that is to make sure there's a range of head plates we can use with the vessels in order to accommodate different probe types, different feeds and gases and so on and so forth. So we do offer a good choice of standard designs with a large number of ports and port sizes and the arrangements of those ports, and we also have the ability to offer customized designs. So if your application needs something a little bit special or something, or probe in particular, or probe arrangement, we can customize something for that. further to the information content is, unlike some other suppliers, we're not restricted in the probes that people use on the system. So although we can recommend certain probes for a specific application, we do take into consideration client opinions, and some have strong opinions on the probe design they want, or the probe type. That's based on past experience, or perhaps probes they use at a larger scale. So the Xplorer HT system and the electronics and the software is designed to use any probe type. So as long as it can record something, we can record that data in the software, and also plug in feedback loops and that kind of thing. So what we're aiming for is to offer a small bioreactor with a large information content. Here is just a typical example, just to demonstrate that principle to you. Here's a 100 ml reactor. It's got a square head plate. This does have some bearing on a later slide, but we have a selection of different designs and different shapes. So here we have 11 ports. 4 of them are dedicated to different probes. Then we have a gas sparger, different feed lines for liquids, sampling port, a condenser to maintain volume, and here you can place a pressure monitor or a gas analysis tools, and finally a nitrogen inlet as an option. So at the moment we feel this is the smallest classical style bioreactor available, and indeed all our miniature bioreactors can be populated in this way. One notable tool is an online cell density probe that we use. We call it BioVIS probe. It's a probe we've developed, and it's really beneficial to our clients to be able to monitor biomass during a process without the need to take samples. This not only reduces time, but it also avoids the risk of contamination by opening the sample port. So you can see here a comparison between offline optical density and the data taken from the probe. You can see a real close correlation. The bottom graph shows the results of 9 separate fermentation and sterilization processes, and demonstrates the robustness of the probe over many cycles of as I say, sterilization and fermentation. The BioVIS probe is actually available as a standalone system, so can be added not only to our systems but also to third-party systems as well. Because the system is designed to accept multiple bioreactors, we have different blocks available that can be placed on the bioframe. So here's the block position, and onto this you can place either a 4-zone block, 2 4-zone blocks, or a 1 8-zone block. And those blocks are within a 50 by 56 centimeter footprint. And so the design is really to ensure that you get the most out of valuable bench space, and you also get as many bioreactors into that bench space as possible. So this just demonstrates the blocks positioned on the frames. So we have the 4 version, the 8 version, and as I've said previously, it is possible to have litre scale systems on the platform. Now the advantage of this is you can reuse many of the electronics and of course the software and liquid feeds and gas feeds on litre scale systems as you do on the miniature bioreactors, so you can interchangeably swap both blocks, sizes of vessels and litre. To some degree, of course, you have to replace probes and perhaps increase liquid feed rates and so on, but what we want to do is make sure there is a good possibility for upgrading the system with as cost effective as possible. So at the moment this is the largest range of bioreactors that you will see on a single platform. Now the other advantage of the blocks being separate from the bioframe is that they can be placed onto any liquid handling robot. So liquid handling robots from Hamilton, Tecan, Beckman and many others can accommodate these blocks as part of an integrated system, and this really gives significant advantages for being able to do upstream and downstream processing, sampling and inoculation functions. So for an example here, we've got this housing covering the whole system. We can, this example shows micro plates that have been used for seed plate purposes, so they samples are taken to inoculate the bioreactors. Here we have the bioreactor positions, they're fully instrumented, and you can see in the middle there's channels for the liquid handling to take place. You'll notice also that the lids are square. You saw the square lid variants before. This is so they don't move in place. We have the automated sampling and inoculation, upstream and downstream processing modules such as centrifuges, incubators, analytic tools and so forth. And then the deck obviously allows you to house all these resources, and there is some degree of flexibility in swapping these resources in the future. So at the moment, I mean, there are other options on the market, but this really is the only system where you can integrate those resources that you need for your specific application. One key thing about using multiple bioreactors is to ensure reproducibility and consistency between the bioreactors. Now, all the fermenters that we've been talking about are completely independent for pH, dissolved oxygen, temperature, stirrer speed, pressure, which we'll come to, and aeration rate. So if we keep all these things the same, then the growth profile between the fermentations should be the same. The next slide shows data from 4 parallel fermentations on the 4-zone block. And as you can see from this data, there is a real similar correlation between the graphical data. And if you look at the specific growth rate and also the final biomass concentrations, they're more or less identical. Again, we've done many tests, both on the 4-zone and 8-zone blocks, to ensure that these profiles are identical. Just to talk about some of the integrated properties of the blocks. Firstly, temperature control. As I've said, a temperature control between each zone is completely independent with electrical heating, and there's a resolution of 0.1 degrees C between them. And the operating range of the block, which may surprise you, is between -60 and 225. Now this comes from the chemistry automation, but we've left it in place, and it has had some advantages. One being that with stainless steel vessels there is an option to steam in place inside the zones rather than autoclaving. Other clients have found other ways of taking advantage of the wide temperature range as well, outside the relatively short range of the fermentation. Inside, built into the blocks are the magnetic agitators, so you have individual magnetic agitation for each zone, and this allows a speed range of between 50 and 1500 RPM. We give and offer a range of stirrer designs from Rushton for microbial to pitchblade for mammalian, and also a range of other choices depending on the application and what the client needs. And we also offer mechanical overhead stirring should the application and the speeds needed fall outside the standard magnetic stirring. Just a couple of volume maintenance tools. One is the condenser. This is a simple click-in-place Peltier condenser, so it just clicks in place around the condenser tube, which minimizes volume loss and can be used on any bioreactor that we provide. In terms of inventory control, we can use foam level detectors and conductivity probes, but we also can use what we call an inventory control. This is normally used on very large scale vessels in the past, and uses a hydrostatic pressure in order to really measure the mass of the contents inside the vessel. And actually this little accessory can be used on any vessel that you may have, so it's a really third party compatible as well. We offer a range of liquid feeds on the system for various liquid feed strategies: pH control, foam management, inventory control, and media addition and fed batch operation. And these can either be peristaltic or positive displacement syringe in nature, again depending also on the pressure application you may have. So the syringe pumps can go up to 5 bar, and if you're going up to 10 bar, we're looking at using HPLC pumps. Dissolved oxygen control is also standard, and this control can be used both at low and elevated pressures, depending on the type of probe we use, and it can be linked in both cases to either stir speed, gas flow of air or oxygen mixes, or both of these parameters. Now we'll come to pressure applications, which we found to be particularly advantageous with gas fermentation methods. They provide optimal conditions for the use of C1 gas as a carbon source. They also do enhance oxygen uptake, and they can simulate head pressure seen at larger scale, and they can also simulate natural high pressure conditions, and indeed we've installed systems used in marine organisms where they're experiencing high pressures at depths, ocean depths. And we go to, on this particular parallel system, to 10 bar, but of course we can go higher than that, but then we have to look at really different probe designs, liquid feed strategy and that kind of thing. So this next slide is a schematic of 8 bioreactors. Now it's shown in linear format just for convenience. Here we've got the gas flow controllers, each individually flowing gas to each of the reactors, and each reactor has got its own pressure monitoring control, so we can set the pressure of the reactor and maintain that pressure automatically with the flow of gas. The gas mix, or indeed the gases you're placing flowing into the bioreactors, is also controlled from the main gas supply. And so this, together with individual temperature and stirring control, allows you to look at the impact of varying a lot of parameters on the system. This is just a small experiment we've done based on more the chemistry model, looking at vessel design and scale of vessel at a 10-fold and 100-fold differential. So we've got 5 and 50 mil vessels and 5 and 500 mil vessels, and looking at the hydrogen uptake profiles of these vessels at the same pressure, and you can see there's a tight correlation of these profiles when these vessels are compared. Before I get onto gas mixing, I just want to cover the software that we offer with the system. The first part of the system you should look at is the Mimic screen, and here the Mimic represents all the hardware you have on your bench, so the reactor itself, the probes, the liquid feeds and the gas management system. Then we have a reactor selector. Here this is an example of a 4-reactor selector, so we have four buttons to click here for each reactor. We do have a 5th button, and that is actually the gas manager, which I'll come to next. Then we have the tabular data, the real-time data coming from that particular reactor. The graphical display, again, this is freely configurable depending on what parameters you want to see at that particular time. And we also have a recipe planner, so you can program in a stepwise fashion different recipes needed to run on each bioreactor, either all together in a global way, or perhaps you have individual recipes for every single reactor. And as I've said, the fifth button here is a gas manager, which I'll come to in a moment. So gas mixing can be quite complex if you're mixing different ratios of different gases, and what we wanted to do was make this as simple as possible for gas fermentation methods. This just shows an example schematic, although we can almost do any kind of gas mix, number of gases, ratios of gases and so forth. So in this example we've got air, hydrogen and CO2. The first tier of flow controllers are the mixer flow controllers, and they flow gas into a mixed reservoir. And at this point there is an option for gas sampling here for analysis, and this can be compared to the off-gas analysis from the reactors if needed. Then we have the distributor flow controllers, which flow the gas individually to the bioreactors, and each of these bioreactors are pressure controlled, so you can set the pressure and maintain that pressure over the course of the process. This shows the software view of that schematic. So here we have the calibrated mixer flow controllers. Now these can be calibrated, each flow controller is calibrated for the gas that it's actually flowing to the mixed reservoir. Here the mixed reservoir is pressure controlled because you do get a pressure drop between the two tiers of flow controllers, so it's important to keep account of this. This shows the distributor flow controllers with what we call a mix factor. Now it's not really possible to calibrate flow controllers as we've done with the first line of controllers because of the infinite variety of different ratios of gas and so on. So what we try and do is apply what we call a mix factor. This is based on factor-based calibration, which is done automatically in the software. And so this is applied in order to ensure that the flow rate of the gas mix is maintained and also is a measurable quantity as well. Now usually in our applications in gas fermentation we provide a constant flow of gases through the system rather than pressurizing and then just leaving. This is so that the composition of gas in each reactor is maintained and kept constant, and this is because the organisms will probably use the gas mix, the components of the gas mix at differing rates, so it's important to keep this composition constant throughout the process. Now that the last slide showed different flow rates and and the different calibrations and so on. If I can just go back to that slide, this particular setup is delivering the same ratio of gases to each of the bioreactors. Now if you wanted to have different ratios of gases going to each individual bioreactor, it's possible. We would just need to engage with more flow controllers, and obviously there's a cost implication there, but what I'm trying to say is it's all possible. So to make it really easy to set those ratios of gases to each bioreactor, what we can do is insert ratios directly into the software. So for example, we have three supply gases, CO2, air and hydrogen. We have 70% hydrogen, 10% air, 20% CO2, and we can just plot those figures and input those figures into the software, and all the mix factors, and the software controls will automatically deal with those gases and gas mixes within the process. If you want to change the ratio of gases, all you need to do is go back into this control and change the ratios as needed. Because we come from a chemistry, automation and process safety background, we have a lot of expertise in the safety elements of the system, which is quite important when dealing with pressure applications, and also the nature of the gases that we often see being used. So the first point is that we have sealed pressure vessels with gas-tight fittings, so any flow in or out of these reactors is completely controlled. Again, we have automated pressure monitoring and control venting. This is all automated in the system. So any venting is controlled by our software, and usually we have the clients vent into in a safe way within the laboratory. If there is escape of gas from the reactors for any reason, we have multiple gas sensors located on the system, and in response to inappropriate gas presence on the system, we have various safety shutdown modes in response to this. So this is usually remote power down of the unit or similar shutdown modes. Just to give you an example of fully configured systems that have already been installed, the first thing to note, if you look at these systems, the frame, the back panel, there's no real standard design. This is because, again, it's freely configurable for that particular application. Indeed, we never sell the same system twice. In this particular example, we have 8 bioreactors, and they needed quite a lot of feeds, liquid feeds going into each reactor, mass flow controllers here. Then we have a 4-zone system at the top. It's hard to see, but these are stainless steel reactors going to 6 bar pressure, 500 ml volume. Again, we have mass flow controllers located in various feeds. Again, you can see that in all cases that the system can be quite busy, but this is because in the 50 by 56 centimeter footprint, you have to have quite a lot of resources available. On the bottom, you have the equivalent system, the 4-zone system, but here we've got glass atmospheric pressure system. Again, we have peristaltic feeds going to each reactor. And then finally we have an 8 reactor system, and this one's operating at 10 bar pressure, and we've got banks of MFCs which are dealing with the gas mixing on the system with mixing reservoirs and so on. So finally, just to summarize the benefits to your gas fermentation methods, what we provide are scalable, reusable reactors, providing high information content. So this really improves process efficiency, reduces development timelines, and ultimately reduces costs. These systems are capable of parallel processing, so they enable you to speed up strain evaluation campaigns and process development. We've demonstrated good reproducibility across all the bioreactors. We try and, on the standard systems, have a compact footprint. This allows you to have more reactors for increased throughput, and also not to crowd too much bench space. The software is designed to offer the possibility of simple setups, even with complex gas management protocols. We've also showed that it's easy to integrate with other automation systems, and this is a valuable element for upstream and downstream processing, and has large advantages to giving a really powerful tool for a complete automated solution. And we do ensure that the systems are designed for safe operation, both with the pressure and the multiple gases involved. Thanks for listening. If you want to contact me directly, my email address is there, or you can go to our website and you can, when you've thought about the presentation and want to ask some questions, I can be available for either on-site presentations or indeed just email correspondence. Now, I've got some questions so far. Okay, we have, will a copy of the slide deck be available? This will be available. This will be available. The webinar is recorded, and a copy of that will be downloadable from our website, so you can listen to it and maybe share with colleagues at your own convenience. Okay, we have another question. How are the reactors sampled during a fermentation? Yeah, we have different strategies depending on the standard systems. We have two possibilities. We have either a really reinforced septum, where we use a high pressure syringe for manual sampling, or more conveniently we have a T-junction which is linked to one of the flow controllers. This allows an aliquot sample to be taken, and then the dead volume within the tube is then cleared with the gas from a flow controller, so that's rerouted into this sampling tube. So you can, and I can send details on that to you. Actually, I should have mentioned that within the presentation. In the terms of the robotic platforms, both with atmospheric and pressure solutions, we do have solutions for both those situations where they're integrated with the liquid handling robot. Yeah, someone's asked about price range. As some of you may gather, it's really difficult to give an indication of this because there are so many things that can be configured on the system. Perhaps the person who has that can contact me directly, and I can give a better answer depending on the needs of that particular person. Okay, we have another question on gas analysis. Yeah, we actually provide a tandem gas analyzer, but this only looks at CO2 and O2, so if you're happy with those two gases, this comes integrated on the system. For gas fermentation, usually the clients want a little bit more than that, so they usually have ideas about gas analysis tools that they want to integrate, which we've already integrated. I can't remember the one they did integrate, but it should be said that we can integrate these tools into the software. Yeah, I've got another question about how much the systems are. Again, if you can contact me directly on the actual configuration, it does make, as I say, there is an impact on price depending on what you have on the system. Yeah, so there is another question here. And can the gas flow be controlled in feedback with any parameter of the fermentation and from an external gas analyzer? Yes, a simple answer to that is yes. As I've demonstrated, dissolved oxygen is one of them. The output to a gas analyzer is another one. These can all be used for feedback loops back to the system in order to respond in a manner appropriate, and indeed you can program what happens in response to these feedback loops yourself within the software. Okay, yeah. Are there any customer application notes or published studies using the equipment? In terms of gas fermentation itself, this is a new venture for us in terms of installing systems. We installed 5 gas fermentation systems so far, so the publications are a little bit light at this stage, as you can imagine, and there's kind of a commercial sensitivity to that. In terms of the systems as a whole, we do have publications, general publications on microbial and mammalian use, and these can be provided. Now I can provide links to you for these as well. Yeah, question about BlueSense analyzer with your system. Yeah, this can be integrated. This is, for those who don't know, BlueSense is a gas analyzer system currently on the market. We can integrate that. Okay, any questions I haven't answered I will get back to, and I'll reply indeed to all of the questions here in turn, probably more fuller than I've explained here. Again, if you want to get back to me direct about any part of this presentation, please don't hesitate to contact me. And thank you again for listening, and